Hey, this is Mr. Weisfeld. Today we're going through Activity 6, Atoms with More Than One Electron. I have a little music going in the background. Maybe that'll make us smarter today. Alright, you got this graph. Please grab it. We are going to be, so put your name on it. Put your name up here. We're going to be working from this graph during this video, and I want you to turn in this video to me when you're done. It's going to have some answers on it. It's going to have some doodling on it. It's going to have some sketches, some crazy like patterns of things that we're going to notice from this graph. All good stuff. That's what we're talking about today. Ionization energies. Can you say that? Ionization energies versus atomic number. So what I've got is atomic number. There's no atomic number 0. You've got 1, 2, 3 through 36. Hydrogen, helium, lithium, beryllium, boron, da-da-dum. On the left side, or on the vertical axis, you've got the ionization energy in joules, times 10 to the minus 19, a very small number. And then along the bottom, you've got atomic number, of course, and we're going to talk about this graph. So check it out. When I talk about ionization energy, it's how much force or strength or energy it takes to remove an electron from an atom. So if you take a look at helium, helium has 2 electrons, 2 protons, 2 neutrons, and it takes a huge amount of energy and effort to get that electron or one electron pulled away from helium. Helium's kind of happy here, but this guy is like straining, he's pulling, it's like next. Contrast that with lithium. Man, it's just the next element on the table. 3 electrons. You could come up and just, it almost gives that electron away to you. Pop! Pluck that electron right off of lithium. What's up with that? So here we go. Let's get started. We're working from page 409 in the book. We're on question number 3A. As I look at this graph of the first ionization energies, I want to answer the following questions. What kind of patterns do you see? How could you quickly relate the shape of the graph to someone who had not seen it? So let's check this out here. Sounds good. Well, it looks like the graph goes up and it goes down very quickly. And then it looks like it goes up kind of gradually, maybe takes a couple of hiccups there. Then it goes down again really quickly, right? From neon to sodium is 10 to 11 in atomic number. And then it goes up kind of slowly with a couple of hiccups. Then it goes down really quickly again. So definitely a pattern there. And then it looks like, oh, and these peaks here, boom, 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 and boom. This time it goes up, has a little bit of more meandering path, kicks a little setback there, but eventually goes up to a peak again. So if I had to draw this graph for someone who had not seen it, it might be hard, but it might be pretty easy after we talk about it a little bit today. So let's keep going here. All right, page 409, question number 3B. So put like this, write this on your paper. Do like number 3B here on your paper, and then say, where are the ionization energies the largest? Say that with me, ionization energies. Ionization energies here on the vertical axis, you've got ionization energy in joules, and the largest one is over here, helium. So let's just circle that one real quick. And then next, of course, largest is neon, and then argon, and then krypton. Those are the largest. I guess actually fluorine is a little bit higher than argon and krypton, so we might need to circle that one, but those are definitely the peaks. So now let's check this out. Where are they? Here we've got lithium, sodium, smallest ionization energies, sodium, potassium. Those are pretty much the lowest 3. There might be a low one here, gallium. We can make a note of that one. But those are the lowest. So next question. 3C. What happens to the ionization energies as the atomic number increases? So check this out. Remember, atomic number is increasing as I go along this way. And we're looking at the pattern in the ionization energy. So what does the ionization energy do? So in general, if I go here from lithium to neon, ionization energy is increasing, and then boop, takes a big jump down after neon, just like here. Hydrogen to helium goes up. Feel free to draw these arrows on your sheet, and helium drops off. And then, of course, from sodium to argon, it goes up like this and drops off at argon. And then from potassium over here to zinc, then a little hiccup, but then another kind of increase as you go from gallium to krypton. So that's what we could say. We could say that ionization energy generally increases as you increase in atomic number. We'll talk about the other exceptions to that in just a second. Okay, group the elements by their ionization energies into 4 periods. So let's see here. What have I got? Lithium is atomic number 3. Grab your periodic table if you haven't got one. Lithium is 3. And neon is 10. Sodium 11. Argon 18. Potassium K is 19. And krypton 36. Group the elements by their ionization energies into 4 consecutive periods. Oh, and then there's hydrogen 1 to helium. So let's see, I'm going to put the periods in. So this is period 1. I'll circle it. This is period 2. This is period 3. And this is period 4. And you know the funny thing, they say periods in quotes in this question only because those are exactly the periods on the periodic table that we are so familiar with. So something is going on here. Let's check it out. Alright, 409, number 3E. So write that on your paper here. I'm talking about 3E. Alright, I'm talking about 3E here. Is there any interruption in the general trend of ionization energy? So interruption means like, oh, excuse me, oh, whoa. Alright, so you get the idea. So you'd think that you could go just up here, straight up, bah, interruption. You'd think this could just keep rising, and then bah, interruption. And actually, there's even some smaller interruptions here, like beryllium. You might think it should keep going, and bah, boron takes a little setback. You might be thinking that nitrogen could just keep going, but bah, there's another little setback at oxygen. So there are little setbacks, but in general, there's this really big setback each time. In other words, a huge decrease in ionization energy over a small change in atomic number. We call that slope in the graphs in algebra. So the graph of this, or the slope of this graph, positive and then very negative. Positive, generally very negative. And that's kind of how I would describe this interruption. In argon, there's an interruption here from zinc to gallium. But if you could look at this graph on another, or you could look at past krypton, you would see there's another big interruption after krypton. So you generally get to these elements and then there's a big interruption. All right, next question. All right, so question 4a, page 409. I'm looking at the second colored graph that we drew, which was a second ionization energy. On your piece of paper, you can turn that over. If you've been looking at the one just single line, you can turn it over and look at this other line. So I'm looking at these two graphs and I'm looking for similarities. So let's see. All right, let's grab my pen here. Let's try to. I rise to a peak, and then I've got kind of an element at the peak, and then I have a huge drop off. Then I have an element at the peak, after a little bit of a rise with a couple of hiccups. Then I have a huge drop, again a rise with a couple hiccups, huge drop off, and then this is kind of a smoother rise, a little bit of hiccup, and then boom, another peak. Let's circle these peaks. And then I actually don't think there's a drop off right at Krypton here because we don't have that data. Hang on. So really similar. The elements at the peaks are different. Look at helium versus lithium, neon versus sodium, argon versus, sorry, that's potassium. I might have said Krypton. I always get those confused. Check this out, zooming in. This is K, this is Krypton. Sorry, potassium. This is argon here. All right. So I see some similarities, and then I also see here that there are some low ones: beryllium, magnesium, calcium, germanium. There are some low items as well. A gradual rise and a steep drop off. That's the general idea. So you could say, let's just write that down if we're writing down these answers. So you've got very similar, you could say. Very similar, huge drop-offs. Writing's not going to work. Huge drop-offs, and you've got some items at the peak, some elements at the peaks. All right, so read this. I'm going to give you a second to read this. If you had to summarize this in a couple words, what kind of words would you say? Would you say, I would say there's some words like stable. I would say a lot of energy. I would say neighboring. So, you know, there are elements around another element, neighboring ones, and there's stable ones, or there's a lot of energy. All right. So we're looking for, let's take this next slide. So 409, number 5A. I couldn't get this circled in black, so check this out. What we're doing is we're looking at which element in the first period, atomics number 1 and 2, has the most stable arrangement of electrons in the atoms. Remember, stable, based on the reading we just did, that short little paragraph there was, which element has a kind of much more ionization energy than surrounding elements. Remember, you're looking for elements that have larger ionization energies than their neighbors. In realities, you're looking for peaks, not just those with the higher values. So check it out. Helium, definitely much higher ionization energy than hydrogen. You might say helium more stable. So that's the first period. Let's go to the second period here. Next question. Which elements in the second period, atomic numbers 3 through 10? So this is what I'm talking about here. Let's go get a color here. Oh, I've got lithium is atomic number 3. Neon is atomic number 10. Which elements seem to have most stable arrangements? So check it out. Well, definitely neon because it has a whole bunch of energy. Nitrogen, look at that, has a little bit of higher energy than either oxygen or chlorine. And then beryllium has a little bit higher energy than boron and lithium. So there's like these little somewhat lesser stabilities versus an overall stability of neon. So you could mark these up or circle these when you're doing page 409, number 5B. All right, next one. All right, which elements in the third period, atomic numbers 11 through 18, have the most stable arrangements of electrons in their atoms? So once again, I'm just reading this thing right here. So now this is sodium is atomic number 11. Yep. And then argon, atomic number 18. And what we're doing is we're going up the graph here. So sodium. Oh, magnesium has a little bit of stability. Phosphorus maybe a little bit relative to the others, but then of course argon has a high ionization energy relative to those atoms immediately around it in the table or on the graph here, you might think that magnesium, phosphorus, argon, they're a little bit more stable than their neighbors. All right. And now let's do, in the fourth period, 19 through 36. That's potassium through krypton. So here we go. All right. I'm at potassium, and I'm going through krypton. Which elements seem to have a little bit more stability than their neighbors? Holy cow, zinc seems to be a little bit more stable than its neighbors. Maybe arsenic in a slight way, but definitely krypton. So we might expect these atoms to have something about them in their behavior or how they react with other things to be like a little more stable than their neighbors. All right, that was 409.5D. All right. Let's define new electron energy sublevels, and they go by the letters S, P, D, and F. S, P, D, F are the names of sublevels. So let's read this number 6. I'll read it to you this time, okay? Check it out. As mentioned earlier, so in the last activity, the Bohr model was not able to account for the spectrum of an element containing more than one electron. A more elaborate model was needed. Remember, because the elements got more complicated. In this new model, the energy levels are broken down into sublevels. When these sublevels are filled, that means when we put electrons into, like, think of these as like empty seats at a table that we're putting electrons into. So we're filling those with electrons. As we fill those, the atom exhibits a higher degree of stability. In this model, the sublevels are designated by 4 letters, S, P, D, and F. The periodic table shows the atomic number, the chemical symbol, and how many electrons in an atom. So we've got a new periodic table, and this new periodic table is going to show some of the stuff we're familiar with: atomic number, chemical symbol, how many electrons are in an atom, but also now how many electrons are in each sublevel. The total number of electrons is equal to the atomic number of the element. That's what equal to the protons. So a number of electrons, atomic number, number of protons, all of those are equal in atoms that are neutral. And that's what we're saying here, that atoms are neutral. They have equal to the number of protons. The arrangement of electrons in each sublevel will be referred to as the electron assignment or electron configuration. So we're going to string together some letters and numbers, S, P, D, and F, and then we're going to call that an electron configuration. So check this out. All right. So here's that new periodic table I was talking about. It's got a little more information here for each element, and in particular, here's the chemical symbol. We're familiar with that. Here's the atomic number, also equal to the number of protons, also equal to the number of electrons. We've got the average atomic mass. We're familiar with that. We're familiar with the name of the electron, but this is the new stuff. Electron configuration. What the heck? All right, that's what we're going to talk about. So it turns out hydrogen has a level 1. This is level 1. Has a sublevel S, and then has a superscript that's a number of electrons, a number 1. So that's just a brief introduction to how we're going to use this periodic table, and it's the answer to 6A. All right, so actually, let's go to this one first and then let's go back. So say this with me. Hydrogen 1s1. You're not saying it. I'm telling you to say it, okay? Hydrogen 1s1. Okay, good. Helium 1s2. Lithium 1s2, 2s1. All right, and we're going to talk about why this pattern goes like this, but let's just get these down right, how we say this. Beryllium, so you don't say 1s squared or to the first power, you just say beryllium 1s2, 2s2. Try that. Beryllium 1s2, 2s2. Good. And boron 1s2, 2s2, 2p1. So notice there's also a couple more letters. Remember the D and the F? We're not going to talk about those right now, but we're going to come to them in a second. So this is like a piece of these electron configurations. Remember, this is called an electron. Sorry, this is called, I'm pointing at it, you can't see it. This is called an electron configuration. So 2 is the level. P is the sublevel. And 3 is the number of electrons. So once again, level 2, sublevel P, number of electrons 3. So when I say 1s1, that's level 1, sublevel S, electrons, 1 electron. So check it. Right here, this is the number of electrons in hydrogen. You add up these little numbers on the superscript number. So lithium has 3 electrons. Beryllium has 4 electrons. Boron has 5 electrons. That's all there is to this, okay? So let's go back to this one right here. So number 6a. In what sublevel are the electrons in hydrogen? We just did that one. And helium. So helium, we're looking right here. We're looking right here. Let me circle it. 1s2. Bam! Helium. All right. So that's all we're talking about when it comes to sublevels. And then let's answer a couple more questions. In what region of the periodic table are electrons added in the S sublevel? So it turns out you're only going to add S sublevels in this region right here. So in group 1 and 2. That's the only place where you're going to add S, because look, it goes 1s1 or 2s1 and then 2s2. Or 1s2, but these are both 1s2, 3s1, 3s2. That's the only place where you're adding S's. Alright. Then, what region of the periodic table are you added in a P sublevel? This is page 496C. So it turns out you're only adding electrons in the P sublevel here in this part of the table. So this is groups 13 through 18. And the number of electrons, look close at this here now. It says 2p1, 2p2. I'm looking at the last little bit here. 2p2, 2p3, 2p4, 2p5, 2p6. So P can only have like 6 electrons. So the P sublevel can only have 6 electrons. Let's go to the next one here. In what region of the periodic table are electrons added in the D level? So here we go. Here's the D level. It goes like this. It goes D1. So 4s1 is potassium. 4s2 is calcium. But then you have 4s2 and then you add the 3d1. So 3d1, 3d2, 3d3, 3d5. That's weird. 3d5 again, 3d6, 3d7. Turns out, if you look at these, you have the D levels go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So the next question in the book was, where do you add the D levels? Here you add the D levels in this section of the periodic table, the transition metals, and then that's green. And then where do you add the F sublevels? It turns out you add the F sublevels down here. And these are called the Lanthanide Series and the Actinide Series. So once again, S sublevels here, only 2 electrons. P right here, groups 13 through 18. This is just another periodic table, just a quick view. Notice the color here: P yellow, orange, sorry, S red, D green. D sublevels are added here. D has 10, and then F sublevels, F has 14. All right, and then real quick, let's just look at, so that's magnesium. Here's magnesium. Then here's iron. Look at how iron goes: 1s2, 2s2, 2p6, 3s2, 3p6, 4s2, 3d6. It's almost like the street address for electrons of an atom. Pretty cool. All right, so that's all we wanted to talk about today. Thanks for paying attention. Have a great day.